Yeah, thanks for having me. Thanks to the organisers. I'm going to talk a little bit about some work that I've been doing relating the optical turbulence profile and tomographic reconstruction for the ELT. So we'll talk a little bit about the motivation behind this, and I've got a sort of slightly rubbish flowchart. And I'm going to start from the right-hand side of this flowchart and make the slightly the not very controversial statement that we want to do good science. And one of the things that feeds into doing good science with our telescope is having a good tomographic reconstructor. And I appreciate that in this arrow there is a lot of stuff that goes on here, like a whole AO system and a big telescope, but we'll gloss over that. And so the tomographic reconstructor is basically should give in a tomographic AO system should give the optimal reconstruction of the turbulent phase altitude from the many wavefront sensor measurements, and the responsibility of computing the tomographic reconstructor is given to the soft real-time control system or the supervisor. And this computation actually can be quite significant at ELT scales, depending on the exact reconstructor that you're trying to compute. But the SRTC takes in information from a lot of different sources in order to compute this reconstructor and in order to give us good science. If these change, then you need your soft real-time control to update your tomographic reconstructor to maintain good science. And most of these things are well known, and they can be predicted for an observation, such as the change in geometry of the system, or the noise, things like that. But the optical turbulence profile changes in an unpredictable way, and that's because it's basically weather. So it's a weather kind of effect, so you can't predict it. You can forecast it, but you can't predict it exactly over the course of an observation. So what I'm doing here is just looking at how the changing turbulence profile affects tomographic reconstruction, because these effects are unpredictable and largely unknown. And the effect of your turbulence profile in your reconstructor not matching your true profile is that there'll be an increase in error, and so a degradation in your AO performance. So I have two questions I'm going to answer. First is, how many layers do you need to reconstruct? So the reconstructor has a number of discrete layers. And also the second question is, how often do you need to optimize to keep up with the atmosphere, which is constantly changing? So what we use is a fast Fourier tomographic AO simulation, which we couple to a large database of turbulence profiles to answer these questions. So the large database of profiles that we use is the 2018A database from ESO Paranal. So these are high resolution 100-layer profiles. There's over 10,000 of them measured by the stereoside. And we feed every profile through the tomographic AO simulation, and we compute a tomographic error, so basically the error in the reconstruction of the phase. And what we do is we compute this multiple times. So we compute it with, for example, with optimal, in the optimal case, so where we're reconstructing all of the 100 layers, and we're reconstructing that exact profile. And we compare that to the case where we're reconstructing only n layers, so a fewer number of layers, and there's been some time for the profile to evolve since you last optimized the reconstructor. So the simulation setup is so we use the Lamb Fourier code, and that means we can simulate a single turbulence profile in a few seconds at ELT scales, and the whole data set takes about 20 minutes, so it's pretty quick. I don't need to tell most of you, I think, what the ELT parameters are. So we're using 6 LGS in a circular asterism, and we set these LGS in 3 different sort of diameters. So we're diameter 1, 2, and 4 arc minutes, which correspond approximately to LTAO, MTAO, and MOAO. But obviously, we're not going for any particular system. We're just trying to kind of explore the parameters of the space a little bit with these 3 asterisms. Firstly, what we do is we actually simulate a worst case. So we define that as the increase in tomographic error that you get if you just use the ESO 35 layer profile as your optimization profile. And then so that what you get across the 10,000 real profiles is you get these sort of distributions of tomographic error. This is for the 1, 2, and 4 arc-minute asterisms. So the idea is if our tomographic error at any stage is worse than this, then we shouldn't bother, because we might as well just use a median profile. And it's worth saying as well that we get similar results no matter what median profile we use here. So these results are kind of quite generally applicable for if you just ignore the changing in the profile and you just use a single profile for all of the time. So how many layers do you need? So we use 3 different methods to compress the profile from the full 100 layer profiles down to n layers. We have the equivalent layers, which maintains the isoplanatic angle. We have optimal grouping, which has been shown to be quite good in end-to-end simulation, is a bit more involved. And then we have fixed layers, which is exactly what it sounds like. We just basically rebin the profiles into the same fixed layers for every profile in the data set. So you can see an example on the right here of taking this black 100 layer profile and binning it into 8 layers with the 3 different methods. You see that in some places the layers line up and in some places they don't, so there's some agreement and some disagreement. And the point is which of these is best and how many layers do we need. So we put these through the simulation and we get some results like this. So for all these plots, the solid line represents the median of the 10,000 profiles, and the darker shaded region is the interquartile range, and the lighter shaded region is the 5th to the 95th percentile range of increase in tomographic error. And we also have the grey lines here, which represent our worst case median solid line and the interquartile range, which is the dashed line. So going from top to bottom here, we have our 1, 2, and 4 arc-minute asterisms, and from left to right, we have our different compression methods. And so we can see, obviously, if you're reconstructing very few layers, we're reconstructing 2 layers, and you get this big increase in tomographic error because the profile in your reconstructor doesn't match in any way the true atmosphere. And then as it obviously goes down as you use more and more layers in your reconstructor. But a more interesting way of presenting this is to say, how many layers do you need to maintain an increase in error below some threshold? So that's what we've got in these plots here. We've got 3 different thresholds. And we have the LGS asterism diameter along the x-axis here. And then on the y-axis, we have the required number of layers to stay below this threshold. So this left one, we have 40 nanometers RMS, increase in tomographic error. So we say the solid lines represent meeting this threshold 50% of the time. And the dashed lines represent meeting this threshold 95% of the time. So the dashed line is a much more robust system. And so if we only want to meet the target 50% of the time, we need 5 optimal grouping layers, or 6 equivalent layers, or 7 fixed layers at 1 arc minute. So that's pretty, they're pretty similar. But if we want to meet it 95% of the time, it's 8 layers for optimal grouping and equivalent layers, but it's 14 for fixed layers. So fixed layers, you need far more fixed layers in order to meet that error budget. So moving on to the how often you need to update the reconstructor. Obviously, when you update, you optimize your reconstructor, then the profile evolves over time, so it doesn't match what's in your reconstructor. And that can lead to a degradation in tomographic error. So what we do is we split the whole data set into 1-hour chunks. We are optimizing once per hour, and we get some sequences like this where, so on the top here, we have a sequence of turbulence profiles over a few hours, and at the bottom here, we have the tomographic error. And so the blue is the optimal, so we're optimizing on each of these profiles as they come in. Orange is our worst case, so just using the ESO 35 layer median. And green is if we optimize at these vertical dashed lines. So we can see for the most part, the green does fairly well at staying close to the optimal. But then here, what happens is you optimize here and then 2 layers appear, one at 5, one at 15 kilometers. And suddenly your tomographic error, which should be in the optimal case up around 90 nanometers RMS, is actually over 150 for a short amount of time and then goes back down again. So over the whole data set, we average this. You get something like this. So again, this is the 1, 2, and 4 arc-minute asterisms. And this is the increase in tomographic error as a function of the time since you optimized your reconstructor. We see that most of the increase actually happens in the first 20 minutes after you optimize, and then it sort of plateaus off. And it's a very similar shape for for each asterism. It's just the numbers are obviously bigger as your asterism gets wider. And it's also worth noting that even after 1 hour, you're still usually better than the worst case. So it's usually better to optimize on a profile from up to 1 hour ago than it is to use a median profile or something in your system. And again, we can kind of invert this. We say how much time passes before we hit some threshold increase in error. So these plots again are for the 3 asterisms, and these are cumulative probability lines. So say if we take the 20 nanometer threshold for 1 arc minute, in the median case, so where this crosses 0.5, we're hitting 20 nanometers after 20 minutes. But there's a small number of, so 10% of cases we're hitting it after less than 5 minutes, and then another 10% of cases we're hitting it in over 1 hour. So there's a big spread in this time that it takes to reach a threshold for any of these given thresholds. So the answer of what is the best optimization period obviously depends on how much error you can tolerate, and also your desired robustness. So do you want to manage to get all of these cases where you're hitting 20 nanometers after 10 minutes, or are you okay to make the gamble and let it run for longer? So this led us to look at some optimization strategies where we take 2 contrasting nights of profiles. So one where the profile is very variable and one where it's more calm, so less variable. We compute the tomographic error for the night using different optimization strategies. What we do is we introduce a strategy where you optimize the reconstructor only when you meet a threshold in tomographic error increase. So what that means is that the optimization period will actually be changing dynamically depending on the state of the atmosphere. So if your profile is changing a lot, then you'll be reconstructing quite fast. Whereas if it's calm, then you can leave it for hours and it will be fine. Yeah, these results are for the 1 arc minute case, but these are the kind of plots that we get. So again, we have a sequence of the whole night of turbulence profiles. This is the night where it's more variable. And then we have these 4 different optimization strategies here. And then at the bottom here, we have the optimization times. So this is the vertical line represents a time where the reconstructor is being optimized. So for these 4 plots, we have tomographic error over the night. And for each of the 4, we have the solid black line, which is optimal, and the dashed black line, which is the worst case. And then we have these 2 cases here where you're optimizing every hour. But this case, you're lucky in that you happen to optimize at the right time such that your error stays fairly low. Whereas in this case, you're optimizing exactly the wrong time. And it means that you get these big spikes in error that you obviously want to avoid. And the difference is only 15 minutes or so in an offset. So there can be a big difference in performance as to whether you're unlucky or lucky with your time that you're optimizing. Obviously, if you choose a very short optimization timescale, 10 minutes, then you actually do fairly well at staying close to the optimal. And finally, our threshold optimization, if we only optimize when we reach 40 nanometers additional error, does about the same as 10 minutes. But we can see that we're optimizing much less over the night. So whereas for 10 minutes, we're constantly re-optimizing. For this threshold, we're actually can leave it for an hour at some cases, but at other times we're going very fast. And then by contrast, this is the calm night where we have a much less going on in the profile. And actually there's less of a difference between being unlucky and lucky in the 1 hour case. And actually you could almost set a constant period of 1 hour and you do okay. And again, the 10 minute optimization is very close to optimal, as is our 40 nanometer threshold. But in this case, the 40 nanometer threshold can leave it for very long. So there's a period here of about 3 hours where you don't need to update anything as regards to the turbulence profile. And your performance is pretty good. So yeah, to conclude, we've looked into some of the implications of suboptimal tomographic reconstruction on the LT scale system. And it's worth noting again that we're only considering this from an atmospheric perspective, so only considering the changing turbulence profile. Obviously, there are many things which might constrain the design of your SRTC or how often you need to update. But this is looking at it only from a turbulence profile perspective. How many layers required obviously depends on the LGS asterism and how much error you can deal with. Optimal grouping compression from a high resolution profile gives very good results, but not by much. And you will need some additional layers if you want to operate in 95% of conditions instead of 50%. Similarly, for the how often question, most of the increase in error is occurring in the first 20 minutes after optimization. But even if you go very fast, you can still get these error spikes on very short timescales, as the atmosphere does something that you don't expect. And yeah, so maintaining near optimal correction requires either a very short update period or this variable update period where you update and you keep your tomographic error below a threshold. Thanks very much. If you want some more information, there's a paper that was published in May this year. Yeah, thanks.
Okay, thank you very much, Ollie. Really interesting talk. So just to remind everybody, if there are any questions that anybody wants to ask, then there is the turbulence profiling Slack channel that people can ask questions in, or if you're feeling brave, you can raise your hand in the chat window and I can call on you to speak your question in person. So while we're waiting for some questions to come in, I'm just wondering, Ollie, so have you considered how some of these update rates would change if you change between targets? So either just basically from a different direction, which I guess is more difficult, or from the change in zenith angles?
Yeah, so I have looked at, so obviously, yeah, one way in which the profile would change is that if your zenith angle is changing over the observation, and that is a predictable source of error, as it were, because you know how the zenith angle is going to change. So there are plots in the paper where it's showing how the or a plot in the paper showing how the tomographic error changes with zenith angle. As for changing targets, I'm not quite sure. Yeah, obviously you have to update faster if you're pointing low zenith angle. Yeah.
Okay, and then I was just wondering, when you were running through this this limit of having kind of the 40 nanometer RMS error, what were the kind of the fastest update rates that you were having to get to when you set a limit on what tomographic error could be?
Yeah, so you're talking about these kind of yeah. So you can actually so sometimes you do update on a time scale that is very short, so two minutes or something. That happens once here actually, where you pretty much immediately have to re-update the reconstructor. That obviously would be is a challenge from an SRTC perspective, I imagine. But yeah, like I said, for most of the time you can actually leave it for longer, for periods of hours. So whether there's something you can do there with the sort of the long time in between updates of the profile, that you can do something else to help with your very fast update.
So, question from Johan Kolb. How would you suggest to measure the increase in tomographic error in real time from onboard turbulence profiling, wavefront sensor residuals?
Yeah, so what we would envisage is that a tool such as the Fourier simulation that we've employed here could be used, and then every time a new turbulence profile is measured, it's fed through the simulation, and it gives you a number of tomographic error, and you compare that to what you theoretically have at the moment, and then use that for your thresholding. Yeah.
And another question from Carlos. Have you factored in the fact that the CN² profile can only be estimated so well from the telemetry?
No. So this is assuming that when you optimize, then the profile is known perfectly. So I guess, yeah, probing those sort of questions would require, some profiles from telemetry and some separately measured profiles that you think are correct, which would be a challenge.
Yes, what is the truth?
Yeah.
Okay, well, and if any more questions come in, I'm sure Ollie can answer them in the chat. Otherwise, we'll move on. So thank you very much, Ollie.